Hey everyone, today we are going to look at methods for ether synthesis. Ethers are mostly non-polar molecules that involve a carbon bonded to an oxygen bonded to another carbon, and as a result they don't take part in a lot of the reactions that we've learned up to this point because they are neither acidic, basic, electrophilic, or nucleophilic. So for this reason they make excellent solvents. The first method for producing ethers is called intermolecular dehydration. Okay, so this involves an alcohol first being protonated by a strong acid, like H2SO4 in this case. The alcohol, which is weakly basic, would react with the acid. Okay, this forms a protonated alcohol with a strong leaving group, OH2. So this molecule is readily attacked by a nucleophile, such as another alcohol. This would be an SN2 reaction in which the molecule of water gets kicked off when this alcohol reacts with the alpha carbon in our original protonated alcohol. Okay, so this forms a protonated ether. And this protonated ether could easily be deprotonated by a water molecule to form our final ether molecule. A few notes about this process. First is that our product was a symmetrical ether, ROR, such as diethyl ether, dimethyl ether. It wouldn't work well to produce asymmetrical ethers, which would require two different alcohols to form the product. It's an SN2 reaction, and we learned that SN2 reactions are always in competition with E2 reactions, which would form alkenes as side products. Now, there are ways we could favor SN2 over E2. One way is which we could use lower temperatures, but we still have to use high enough temperatures for the reaction to actually proceed. Also, we can use unhindered primary alcohols. So this is not a viable process for making ethers from tertiary alcohols. And even if we were using secondary alcohols, we would still get a significant amount of side products, which may make it not the most desirable method to use in those situations. A second way to make ethers, which we have actually done before, is called Williamson ether synthesis. Right? So this involves an alkoxide ion reacting directly with an alcohol to perform an SN2 reaction. And unlike intermolecular dehydration, this allows us to produce asymmetrical ethers because we can choose a nucleophilic alkoxide ion and a substrate alcohol. The alkoxide ion can be produced from an alcohol by reacting it with a strong base. Hydride ions are very strong bases capable of deprotonating primary alcohols and producing hydrogen gas as the byproduct that's easily removed, although some alcohols will react with NaOH as well. The alkoxide ion would then attack the alpha carbon on a substrate that has a good leaving group, like bromine or a sulfonate, which would form our ether. One thing that's interesting with this reaction is that we can actually make cyclical ethers if we start with an alcohol that has a halogen group. Here's an example of the formation of a cyclic ether. This reaction would have been initiated by reacting a strong base with this alcohol. Cyclic ethers are also called epoxides. The smallest epoxide would form from a halohydrin that contained only 2 carbons. Okay, in this example, we see an epoxide forming just a 3-membered ring. Okay, this would be a very reactive substance because of the steric strain within the ring. Remember, a 3-membered ring has bond angles of 60 degrees, which is quite far from the ideal 109.5 that would be preferred by the electron geometry. Epoxides react readily in basic solutions to form ethers with alcohol functional groups. So an alkoxide ion that could be generated from an alcohol with a strong base could attack one of the 2 alpha carbons in the triangle. Okay, this will open up the ring, forming an ether product. And this resulting ether product would then be protonated by an alcohol. Right. This reaction would result in the original alkoxide being reformed, along with a new alcohol product with the original ether group. Okay, so this would allow the reaction to continue again. In an acidic solution, the epoxide itself can be protonated by a hydronium ion. Okay? This results in a positive epoxide that is open for attack by even weak nucleophiles like H2O. H2O then could open the ring similar to the reaction above. The difference is now we have a molecule that has effectively two hydroxy groups. The bottom one is protonated, but could easily be deprotonated by another water molecule floating by, resulting in a 1,2-diol product. Okay, so these are two different ways that once the epoxide is formed, it could be reopened to introduce an alcohol group or two alcohol groups in the case of an acid catalyzed reaction. Right? If you have any questions, please let me know via email or on Google Classroom. Have a good one.